This video is going to be the first one as we start our journey into our next unit on integration, notation, and techniques. Starts out with a couple of quick sections on notation, then it moves into the integration techniques. So this first video is going to focus just on notation and integration and what it actually means. All right, so we're going to start out talking about something that they'll refer to as the Fundamental Theorem of Calculus, often abbreviated FTC. If you see that notation somewhere, they're referring to the Fundamental Theorem of Calculus. Well, I'm not going to get too involved in this other than to tell you that I think we've discussed enough about about integration to realize that when we're evaluating integrals, what we're actually finding is areas below curves. We've also realized over the last month or so that integrals are also antiderivatives and can be calculated using antiderivatives. Just going on that notion of area below a curve being an integral. So if I have this notation, it's saying determine the area below the curve, whatever this is, starting at A, ending at X, whatever A and X might be. If F happens to be a positive function, then G of X would be the area under the graph. So you can see down here, from A to B. Here's a picture. So this area below here, this area below the curve is the integral of f of t dt, starting at a left bound or a lower bound of a, finishing when you get to your upper bound of x. All right, so that's the first notion we should make sure we understand, that integrals represent areas below curves. That's often tied into the first part of the Fundamental Theorem of Calculus. These are real common questions on advanced placement. So it says, given this function down below, where g of x is the integral from a to x of f of t dt. So if I did g at 0, so that means replace x with a 0. So it would be the integral from a, the left edge, which is 0, up to the right edge, which would be 0, of this function f of t dt. So then I would be saying, well, what's the area enclosed below this function, starting at 0, ending at 0? Well, that's kind of a redundant question. That would be nothing. That would be starting here, ending here. You'd have nothing other than a speck down there where you started. So that one's really easy. That's a 0. G at 1 would be the integral. Left edge is 0. Up to, now I'm going to replace x with a 1. So it's going to be 0 to 1 of this function dt. So that's telling me go find the area below this curve between 0 and 1. Sure enough, 0 to 1. Well, the nice thing about that particular region is it is a nice easy triangle. I could get the area of that just by going 1/2 the base times the height. So the area below this curve would be 1/2 base times height. G at 1 would be equal to 1 then. G at 2. So now it's the integral from 0 to 2. I'm going to stop writing this all out. I just want us to get that connection that it's the area below the curve between 0 and 2. So now I'm going to go from here all the way over to here. So I had this already. I knew it had an area of 1. Well, now I'm just going to add this piece to it. So that rectangle that I've added to it is 1 by 2. So it has an area of 2. This triangle had an area of 1. So G at 2 must be 3. G at 3 is going to involve us doing a little bit of estimating, because, so I still have the 1 here plus this area, which is 2. Here's the problem though, I've now added this piece in as well. Well, the problem with this piece is that it's not a perfect triangle. So you can see that this closed in region is more than this one. So it's 1 for sure, because if it was a straight line down there trying to be 1. And then I'm going to say I wouldn't say it's half. You know that if you put a line here, look at this over here, this triangle has an area of 1. Well, that triangle that's not shaded in also has an area of 1. Well, if you say, well, what fraction of that triangle did I shade in? Well, I don't think it's half of it, so I'm going to say that I'm just adding on here approximately 1.2. There's really no wrong answer per se here, but I mean, if you said 1.8, well, I'd say you clearly need to reevaluate your estimation. But if someone said 1.3 or someone said 1.1, well, it's hard to argue with it. It's an estimation for this one. These two I could easily calculate. This one I had to estimate. So my answer here would be 3 plus 1.2, 4.2. All right. Next one in our list, I think, was G at 4, if I'm not mistaken. So now we're going to do G at 4. Now pay attention close to this one. G at 4. G at 4 wants us to take what I have up here already, which is 4.2, and now I'm going to bring this piece here into the mix. Now, fortunately, we've studied enough area to remember that down here, if you calculate just the integral, it's going to give you a negative value. Therefore, I'm going to have 4.2 plus this area, which I think you'd agree is the exact same as this piece up here. So whatever I called this, which was 1.2, well, this will be the same thing, except it will be negative because it's down below, which will give me an area of approximately 3. Actually, I shouldn't want to say approximately. It'll be exactly, because as long as you realize that this and this are the same, one positive, one negative, they're going to wipe each other out, leaving you with this piece over here, which we know is 3. And then last but not least, G at 5. All right, so starting from 0 all the way to 4, we've said we're at a total of 3. Well, now I've got this piece down here left to add into the mix, which I think you'd agree is the same as this one and this one. So it is going to be a negative again. So I'm going to take the 3 that I had when I got to here. Now I'm going to add to it another negative 1.2, which will give me a negative or a positive 1.8 roughly. So that is how you determine areas below curves in the context of an integral, paying attention to whether the area is above or below the axis, what shape it's taking on, whether you have to estimate, so on and so forth. But as I said, those are a really common multiple choice type question that they like to use on advanced placement calculus exams, just to see that students draw that connection between area below a curve and an integral. All right, so that's the first thing I wanted to address. Second thing in this video I want to talk about is the notation where an integral is found by taking the antiderivative. So I want us to kind of draw the connection that integration and differentiation are essentially inverse processes of each other, sort of like multiplication and division. One undoes the other. Addition, subtraction will undo addition. Well, if you have an integral and you wanted to undo the work of an integral, you would take the derivative. If you wanted to undo the work of a derivative, you would take the integral. They are opposite processes of each other. Now, we're going to focus on something called Leibniz notation. It is not something used extensively, but you will run into it from time to time, so I think it's worth us at least mentioning. You usually will see it, again, probably in a multiple choice setting. I've sometimes asked it as a quick little question on a midterm or something, but once you kind of get the gist of how this works, it's really easy to do. It looks kind of complicated in the beginning just because of all the math symbols and things that are involved. Hopefully we're starting to get more comfortable with those. All right, so if you looked at this, if you saw just this symbol right here, well, hopefully you've done enough calculus up until this point that is the symbol that we use to take the derivative of something. So for example, if I just wrote down dx cubed with respect to x, I hope that you would realize that that wants me to find the derivative of x cubed with respect to the letter x, and the answer would be 3x squared. That's the derivative of that. So this is saying find the derivative of this integral. Okay, well, if I want to take the derivative of an integral, let's go down and use an example here. Something easy that we could do. So if I wanted to find the derivative of the integral from 1 to x of t cubed dt, well, let's come over here and let's just do this first, and then we'll do the derivative at the end. So let's find the integral from 1 to x of, oh, let me back up. I got ahead of myself. Sorry. According to this, I forgot to mention the right side of this. If you're going to take the derivative of an integral with respect to x, and your upper bound here is an x, your lower bound here can be any numerical constant, and I'll show you what I mean by that in a second. So it could be a positive, a negative, but it's just got to be constant, the lower bound. Upper bound is going to be just an x. Well, then your answer will just be the function. If you think about that, do the integral. After you get your answer, take the derivative of your integral. Well, that should get you back where you started, because it's the whole idea of integrals and derivatives being the inverses of each other. So let's go down here and see if that's what really does hold true. So according to this here, if I looked at that and just took it at face value, according to that, it's saying that to get the derivative of the integral of some function, all you do is replace the letter t with the letter x. So this one, according to the rule above, the answer should be equal to x to the exponent 3. And we're going to get to the point where that's all. We're going to look at this and we're going to write down x to the 3. We're not going to do any work whatsoever. Just so that I can convince you that this is actually true, I am going to do this one out, showing you how to integrate and then differentiate, and we'll see what happens. So if I took the integral from 1 to x of t to the third dt, I would get t to the fourth over 4, integrate it between 1 and x, which would be x to the fourth over 4 minus, fill in that, 1 over 4. So that's the integral. Then if I wanted to take the derivative of my answer with respect to the letter x, my answer would be 4 onto x to the fourth over 4 minus, this is not an x, this is a 4, minus the derivative of 1/4, which would be 0. This goes back to show you why it doesn't make any difference what this number is as long as it's a number, because all that tells me is that I'm going to get some number here, which means when I go to do that next process, which is take the derivative, we really don't care what the number is, because we know that the derivative of any constant is always going to give us 0. So as long as there's a constant here, any constant, you're always going to get a constant here, which will mean then down here when you do your derivative, that will always be a 0. Well, here, oh, I forgot to take one off my exponent here, sorry. This should have been 4x to the 3. Multiply and take one off the exponent. Get her to practice with their derivatives, spend so long. 4x cubed over 4, the 4's are gone. And look at that, x to the third, which is what we, in the beginning, were kind of led to believe was going to happen. All right, so what I want you to now understand is that this process, or this notation, if you run into it, is going to allow you to instantly go from this notation to the answer. You're not going to need to show all that work like I just did. I did it the first time to show you that it does actually hold true. So we're going to just now look at how we're going to do this. Okay, so let's look at the first one. The answers are beside them, but that's okay. All right, so I got a constant on the bottom. X is my upper bound. I want the integral of some function in terms of some other letter. Doesn't matter. I'm using t, but that could be any letter. And I want the derivative of it. So the answer will just be substitute x for t, and you're done. That's it. This one. So again, imagine this wasn't there. That's the answer. Okay, so this isn't there. We're trying to figure out what it is. So I look this over. Constant is my lower bound. X is my upper bound. I want the derivative of an integral. I have to do nothing more than replace the letter t with the letter x. Done. Well, I think you're probably saying, well, that's pretty easy. So we're just going to kind of expand upon that and say, well, what if some of the little things that we expect might happen do actually happen? So for example, that was all fine and good. What if the upper bound isn't x? What if it's x squared or cos x or something different besides just an x? We're still going to leave the bottom at a constant for now. We will play around with that in a moment. But let's suppose this stays as a constant, and the upper bound is not just an x, it's some other function of x. Now, I have it all done out here. It's kind of like a chain rule. So basically, it's saying if you wanted to find the derivative of y with respect to x, you could find the derivative of y with respect to u, multiply that by the derivative of u with respect to x. Those would cross each other out. And let me back up a second. You may be saying, well, what do you mean by u? So I'm just taking this top bound, and I'm going to switch it out here. And rather than that, I'm going to say, let's let u equal x squared, like you see here. And then we're going to apply the chain rule, which is find the derivative of this with respect to u, then find the derivative of the letter u with respect to x. And what that turns out to be is find the derivative of y, which is your original question, between 1 and u, with then multiply here by the du over dx. Well, this translates to be the derivative of the upper bound. And again, this notation can be a little confusing, and we don't use it a whole lot when we do describe our chain rule, but this is basically what it's saying. If I look at this, this is now what we were talking about earlier. It's from 1, we used x, but it could be any letter. So if it's from some constant to a variable, you have to be differentiating with respect to that same variable. All you do in this situation is replace the t with the u. So that's cos u. Then du over dx would be, what is the derivative of u? Well, this is u. The derivative of u would be 2x. So then you'll see that it just basically models a chain rule. You do it the same way you normally would have, right? So I replace t with the upper bound. My original question, I'll just go back to it, was find the derivative with respect to x from 1 to x squared of cosine t dt. So if I just kind of lay that out and say, well, how do we do it now? The only difference is if it's something other than an x, you still fill it in for the t, but the extra bit is you got to multiply by the derivative of whatever that upper bound is. In this case, it'd be 2x. There's your final answer. And again, this is just a shortcut using what's called Leibniz notation, which is used when you're finding the derivative of an integral. Okay, let me have a look. I don't know if I have another one below that. Yep, here's another one. So let's have a look at this one. So this would be the derivative of an integral from 0 to x squared. So I'm going to replace the letter t with x squared. So my answer should be e to the x squared squared, and then you multiply by the derivative of that upper bound. So if I just clean that up, it would be e to the exponent x to the 4th multiplied by 2x. And we double checked, see how we made out. They just put the 2x in front, but yep, same thing. Okay, so we're starting to get rolling here now with our Leibniz notation. Here's another one. Find the integral from 0 to 5x, constant on the bottom, function on the top. So we replace the letter t with that variable, or that function, whatever it may be. And our answer will be the integral, the square root from 1 plus 5x squared over 5x times 5. Again, this 5 is there because it's the derivative of the upper bound, which you have to add on as a product at the end if it's not just an x. And you can see that is the same thing. So they just squared that, put the 5 in front. Oh, there is a mistake here. This should have been a 5. I remember now that was missing in my answer key. Okay, so that should have been there. And then technically, to simplify it, you could have crossed those two out and just had that over x. Okay, so let's put some twists on things now that we kind of get the basics of how this works. Now we're looking at the scenario where the upper bound is the constant and the lower bound is not a constant. Well, let's just look at what happens if we've done that with numbers, where let's suppose we've switched these bounds. So if I had this one, my answer would be x cubed over 3 from 1 to 3, which would be 27 over 3, 9, minus 1/3. The answer would have been 26 over 3. So this is the exact same integral. The only thing different is I've changed the bounds. So instead of going from 1 to 3, I'm going from 3 to 1. Hopefully you can predict what will happen. So it's still going to be x cubed over 3. Now our bounds are 1 to 3. So the only thing that's going to be different is these are going to be subtracted in the opposite order. So 1/3 minus 9, which will be 1/3 minus 27 over 3, which will give me negative 26 over 3. So anytime you do an integral and you do nothing more but reverse the order of the upper and lower bound, all that happens is you get the same value here, except one's the negative of the other. Well, if I know that fact, and I go back up here to this question now, again, I wish the answer was covered up, but the answer is here in front of us. That's the answer. Let's see how we would get the answer. So it's derivative. So I'm going to do it as if the x were up here, and then I'm just going to switch my answer from positive to negative. So it's going to be 3x sine x. So it's just an x there, so I don't need any derivative of that. And because it's in the opposite order, I'm just going to put a negative in front of it. There's my answer. There's your answer. Okay. Let's have a look at this. I have this on the next page, actually, just to make it look a little better. Okay, here we go. So the last scenario is, what if the upper bound and the lower bound are both functions? So there's no constant on either the upper or the lower. It's going to be a little bit more work in this scenario. However, we are still going to be able to manage it. We'll use this kind of as our guiding principle. Let's suppose I had this question, and I wanted to get the integral from 1 to 3. So I'm going to ask you if I could do this. Could I do the integral from 0 to 3, and then subtract from that the integral from 0 to 1? So if you look on a picture here, so this is the graph of y equals x squared plus 1. Just got a little visual here to help us out. Let's suppose this is, I got my line in the wrong place. This line, let's suppose, oops, this line, I'm just going to draw a new line that's all grouped together. So let's put a new line here. So there's 1, and there's 3. All right, so if this says if you found the integral from 0 to 3, that would be the area below the curve between 0 and 3. And then you found the area between 0 and 1, which would be the integral from 0 to 1. So if you took this whole blue area and you minus this area here, would that not leave you the integral between 1 and 3? And the answer to that question is yes, it would. So you could, anytime you have two integrals like this, go 0 to the upper bound, subtract 0 to the lower bound, and it should leave you the area in between them, which you're looking for. Using that as our reasoning, let's go up to this example. Well, I could write this. I just put my dx out here. And now I'm going to do two integrals. So I'm going to do the integral from 0 to x squared of 1 over 2 plus e to the t minus the integral from 0 to 2x of 1, I forgot my dt here, 1 over 2 plus e to the t dt. And then we're going to do the derivative of those. So we know that that means now notice the difference. The bottom in both of these is a constant, which means I can use my shortcut where I just simply substitute the upper bound for t and take the derivative. So it's going to be 1 over 2 plus e to the x squared times 2x minus 1 over 2 plus e to the 2x, my upper bound's now 2x, times 2. And that would be my final answer. I think I have another one. Yeah, here's another one. It's the same one. Here's one. This one says find g at 1. So when all is said and done, it wants us to put 1 in for x once I find g of x. So g of x is going to be the derivative, the derivative of the integral of this. Well, the problem is these are both functions. Okay, all plugged in, ready to go again. So, as I was saying, we're going to just figure out this using the same kind of rationale I used in the last one. Once I get my answer, that'll be g of x. And then once I get my answer, I'm going to fill 1 in for x in my solution. That'll be g at 1. Now, where students sometimes jump the gun here is they say, well, I'm just going to fill 1s in for these x's in the beginning. Well, it's in that case, it's going to look like your answer is going to be 0 because you're going to get the same number here and here. So we're going to do this out and see what we get for g of x first. So g of x will equal the derivative with respect to x from 0 to x cubed of 3t minus t to the third dt minus the derivative with respect to x of the integral from 0 to x squared of 3t minus t cubed dt, and that will give me, so here, integral from 0 to x cubed, I'm going to replace all the t's with x cubes, so 3x to the third minus x to the ninth, that's x to the third cubed, that'll get multiplied by 3x squared, minus 3x squared minus x to the sixth multiplied by derivative will be 2x this time. So this is g of x. So then g at 1 will be 3 minus 1 times 3. 3 minus 1, I'm just substituting 1 for all the x's. multiplied by 2, which will give me 2 times 3 is 6, minus 4. Final answer for that will be 2. All right, so there's one where I had to use separated into 2 separate integrals so I could get a constant on the lower bound of each of these and then apply my shortcut for Leibniz notation. All right, so I've got 2 examples here of where this question might appear or how it might appear on multiple choice scenarios of advanced placement. The first one is directly using it. The second one doesn't really require Leibniz notation, but it's a neat question to look at as well. So you may want to try these 2 first. So you might want to pause the video and just see if you can come up with the correct answer. I'm going to skip ahead now here to the next couple pages and do out each one of these. Okay, so here are your solutions to each of those. So this one, the key is the word minimum, which surprisingly, say, what? Really? Why is that such an important thing? Well, the only way you get a minimum on a function is if you hit a point like this down here, which means the derivative, f prime, has to equal 0. So you can't have minimums unless the derivative hits 0. Well, if this is f of x, the only place I can get a minimum is somewhere where the derivative of the function, this is your function, negative 2, x squared minus 3x e, I need that to equal 0. That's how you'd end up with a minimum. Well, I'm going to use Leibniz notation. I will get e to the x squared minus 3x squared, multiply that by 2x minus 3. That's f prime of x. So I ended up taking the derivative of an integral. Well, now I want to say, well, where would that function equal 0? So where would, the reason I'm saying this is because that's the only place that you can get a minimum, is somewhere where the derivative hits 0. Well, if you look at it, you say, well, I've got 2 things. And you say, oh my goodness, this is complicated. Well, it doesn't make any difference, truthfully, because this is multiplied by this, and the answer is 0. Well, E is Euler's number. Euler's number is a mathematical constant. Any constant raised to any exponent, I don't care what it is, positive, negative, 0, could never be equal to 0. It's going to be a number. So this function is impossible to ever equal 0. It can't. So the only thing that could ever equal 0 to give you this answer, you must be somehow getting 0 from this bracket, so that when you multiply it by this, your answer turns out to be 0. So as complicated as this looks, it doesn't make any difference whatsoever. The only way to get 0 is solving this. And now that's linear, which tells me there's only one possible place the derivative hit 0. And that was when x was 3 over 2. Now, if there had been multiple answers here, then I'd have to do some other further examining to figure out, well, is it a max, is it a min? The only possible critical value is 3 over 2. That's got to be the place where you're getting your minimum value. So the answer had to be, that's not a negative, that's 3 over 2. That's that first multiple choice. Second multiple choice, it's giving you the integral from a to b of f of x dx, and it's telling you that that is equal to a plus 2b. Now, this is not Leibniz notation. It's just using integration notation. But again, part of this section is being comfortable working with integral notation. Well, if I want to figure out the integral from a to b of f of x plus 5 dx, from our work with areas, hopefully you realize that you can, because this is addition, there's no exponents or anything here, you can separate this into 2 separate integrals. You could do the integral from a to b of f of x, and then the integral from a to b of 5. Don't forget your dx with each of these. Well, this one is given right here. It says the integral from a to b of f of x dx is a plus 2b. So you're going to replace this whole integral right here with what it's telling you in the question that it's equal to. So that's a plus 2b. Well, I'm going to then actually do this way. I can actually calculate this because it's just a constant. The integral of any constant is just that constant multiplied by x, evaluated from a to b, which means it's 5b upper minus lower, which is 5a. There is this part. So when I put that all together at the end, I'm going to get a plus 2b, that's this integral, plus, they were kind to put a plus sign. If they had put a subtraction sign here, there would have been many, many more incorrect answers, because if it's a negative, it's going to distribute through this whole thing. But where it's a plus, I'm going to put it in brackets just to show you what I mean. Do you understand how if that had been a subtraction instead, then this negative would have had to distribute here and switch these signs, and that would have thrown some students off. But they didn't. They were kind to you, gave you addition. Let's tally this up. So I got 2b and 5b. I've got 7b. I've got a plus negative 5a, negative 4a. So there's what I think that expression is equal to in terms of a and b. 7b minus 4a. There it is. C. All right, so there is a look at some notation involving integrals, also discussing the fact that integrals represent areas below curves, also tying into our discussion that integrals and derivatives are opposite processes of each other. Basically, one undoes the work of the other, and we kind of mesh that all together then when we started talking about Leibniz notation and looking at some shortcuts for situations where we were doing derivatives of integrals. That ends our discussion on notation of integrals, and that puts us in the position now where we're going to get ready to start integration techniques. There's not a whole lot of practice you'll run into with these types of questions, so I don't necessarily have a bunch of practice questions. You'll probably run into it again as we do some advanced placement multiple choice practice in the future, but our next plan, so there's no actual work per se to do with these. Our next plan will be to get into our integration techniques, and then we have all kinds of practice questions that will follow along with those. All right, so stay tuned for your next video on integration techniques.